All right. Hello, everybody. Welcome to this week's edition of the Autoscaling Workstream within Working Group Serving. Thanks for joining. Great to see folks joining again this week. We had awesome discussions last week that I would love to continue. I put some preliminary sort of discussion points in the notes document, mainly as follow-ups from what we discussed last week. We can discuss those things, or we can kind of go in other directions. I see some folks from last week are in the room as well. Robert from BLLM, which we had awesome discussions there. I think a few of these topics may be kind of directed at you, so sorry for putting you on the spot, but I would love to cover some of this stuff a little bit more, particularly with respect to this discussion with defining these like critical inflection points. We started discussing that last week, and I would love to dive a bit deeper on this if everyone's okay with that.
That works for me.
Awesome. So the first topic there was maybe like we can kind of recap a little bit what we chatted about last week. Basically, you were describing these inflection points as like a point in time where the behavior or like the stability of the model server changes from one moment to the next based on input or load. Is this something that we want to continue caring about from an auto-scaling perspective? Probably, right?
I think this is the main thing we want to care about.
Yeah, so diving a bit deeper into that, like what do we, what do we look at here? I think our discussion last week kind of left off on using Q as a proxy for this. Like a few other discussions happened over the past week, in particular, a little bit further down in the notes. Evan posted on Clayton's doc with regards to TGI and some of their thoughts on expanding the role of the queue and how things can change as they're improving things. You mentioned this a little bit last week as well with regards to the states of work in the queue. I'm curious what you think here, and Clayton, I see you in the room as well if you have other thoughts.
And maybe one clarification, I think. So it was interesting because somebody else and I were chatting about this afterwards, and I think we had two different perspectives of criticality. So like, I kind of heard like we've got places where you start hitting the roof line. Those are like kind of like the first transition points. What was interesting to me is I think a lot of, and I've seen this like in customers, is just because an accelerator delivers optimal price per or optimal performance at a specific point, I've started to, and I'm actually kind of looking for maybe fishing. I have pretty good exemplars, but not necessarily like complete data that actually most people don't operate at the optimal point. They optimate far, or they operate far past that, because actually it's how much useful work do you get in a period of time, and you can't make progress on an LLM response except in parallel. So it's kind of an interesting, like you could definitely operate, less densely. But what I've noticed is a lot of people operating past that critical point of optimal performance, like where the memory and compute roof lines hit. So Rob, I was actually like curious, are we talking about the same roof line, or are we talking about the same critical points or not? And do you not see people operating beyond that for various reasons?
I think like when it relates to like maximizing out the accelerator, like I actually don't think it's like possible to max out an accelerator in an LLM serving workload because of this like memory boundedness concept that we were talking about last week as it relates to like the decode phase, where like that's where most of the time is being spent, and like the piece of the accelerator that is being maxed out is the memory bandwidth. Like in that kind of scenario, like that's where the bottleneck is. And so like like I guess so I guess for like LLM serving, like there probably isn't like a like I haven't really been thinking about like I don't think there is like control over like maximizing or what was the term you used again of like utilizing the hardware? Like, what was the term you used again?
Balance. I've talked about like balanced or optimal, but like maybe that's not the right word. I
Yeah,
don't know if
yeah.
that's
It's like there is no way to like overuse the accelerator in the context of LLM serving, basically, because like the very shape of the decode phase of inference is like always going to underutilize the tensor cores, and like you're going to be bound in the amount of time being spent moving the weights from main memory into the into the SRAM. So so I don't think like as someone setting up an inference service, like you can't really like target a utilization. You can measure utilization as like a metric of like how well is your system like hitting utilizing these resources, like that model bandwidth utilization or memory bandwidth utilization, and like is kind of like this metric of like how closely am I maximizing like usage of the hardware. But like I don't, and so I think it's like sometimes more of like an aspirational goal to like make MBU as high as possible, to like get the most tokens per dollar in some ways. So I don't know. That was really like unstructured like thoughts. Just like as I think about LLMs, where like you know you, I don't think like people can really like target an MB. I don't think like people make a decision about like I'm gonna choose MBU of 50 versus MBU of 25. It's more like I want to make MBU as high as possible, on my server, subject to like some latency threshold that maybe my application needs. I don't know. Sorry, that was
And I
like
think
really unstructured. I just
no, that's okay. And I think like that's actually what like at the heart of it, I think that was what I've seen, which is people are looking to achieve a latency objective, and there's really only one variable they have. Like there's a couple of there's a bunch of uh, possible variables, but usually what people do is they say like the variables I have are model server, and I'm going to change those until I get whatever one gives me okay. And then I'm going to work with it, I think, as you're saying, what's the optimal that it does, and I'll just accept that. But then the next variable is how much hardware horizontally do I put under it for a given input traffic. And that's kind of what we're talking about. So like criticality and I think in those is there's a point at which you're not even utilizing the full memory bandwidth of the accelerator. So you're not putting enough consistent traffic, like it's all coming in bursts or it's whatever, to keep memory bandwidth saturated. And then at some point, I think this was a great insight from last time, which is a good takeaway message would be, it's the model server's job to take the traffic that it is given and extract the optimal performance that it can. And the model servers expect VLM, TGI, Triton, I think all will have that like mental model. How do we extract the most performance? That's their responsibility. The level above that, I think, is how, as a Kubernetes project, should we think about the problems that almost everyone will have? Like what are the common problems that, unlike web apps, I'm not scaling on CPU. Utilization scaling doesn't make sense. Therefore, it has to be something higher level. What are those higher levels? That was, I think, looking for people to contradict the idea that you're going to have a latency target and you're going to measure, and then you're going to go try to pick a number that a constant out of that. Where that constant is reflected, I think, is maybe this. Like we also talked about criticality. What are the signals that we give to the model server? One of them is what is queue depth acceptable? That's the admission strategy. And then how quickly do we react? And there's reasons like, the interesting thing, and I'm looking also maybe for people, we talk about critical thresholds. The nice thing is that LLM inference does, because queuing is built into model servers, because model servers are doing their best to hide that problem, there's a nice compressibility aspect of inference that is not there for CPUs, where once you hit like a certain point, you start thrashing caches and everything falls apart. You could go build that into web apps. Most people don't. It is absolutely built into model servers, and model server teams are doubling down on that. How do we use that productively as to help operational teams?
Yeah. The only other thing I would say is like, I do agree that it is like the model server's job to like get the maximum memory bandwidth out of, you know, the amount of traffic that they have. And like that is like absolutely what we're doing in VLM. I guess the only thing from like the Kubernetes operation side is like it is definitely true that like MBU goes up if you have more load on your server. Like, and so in some ways, like the thing we're all like trying to get at is like you want to increase MBU as much as, and also like, and this is what I've been trying to get at with this like critical point thing, which is like if you're under that critical point, increasing the load doesn't hurt the teapot too much. Like in between having 32 active requests and 64 active requests, it's not a 2x difference in latency. It's more like a 10% difference in latency for the teapot. And like that is a very surprising factor. And like to maximize efficiency on these systems, it's like we want to put like as much load and concentrate like as much load as possible onto a particular server right up until we get to that critical point, and then we want to like add more capacity, like because the servers, you know, scale really nicely in terms of the teapot as long as we're like under a threshold where enough time is being spent in decode to you know, to not, you know, get things thrashed out from the pre-fill times. So that's why I like the queue time, because the queue time is really the thing that is going to tell us like when we're moving from, you know, the server being healthy enough to like make progress on the decodes into
the server is keeping ahead of its queue versus
exactly.
falling behind in its queue. I think that's a very succinct way, and I think that shows up like, you know, as I was going through and like putting in zeros, it was, you know, there's a shrug in all constant selection. And Ray and I chat about this actually. Like one of the big problems with HPA is that the only way to determine the constants is experimentally, and LLMs are simpler. But like, you know, how do we choose constants? That's kind of like one of the key problems that we're like, critical points are about where the regimes are and what the constants and metrics are that show the transition. So there's the not enough traffic, uh, not enough traffic to saturate, queue depth increasing. That's a nice simplification. Then there's the one which is queue depth increasing and impact to latency of other requests. So it's like a sub one. That would be like if you've got an eviction strategy on the model server, and you know, I think, you know, the nice thing is that if you have queuing on a model server, then you have to have an admission strategy. You have an admission strategy. If we can, anything we can do to standardize admission strategies, or, you know, find the common elements and help encourage them. What is your admission strategy at the next critical point when you start falling behind? Because it's usually too late to auto scale. So the constant of what your auto scaling is has to anticipate that. And it's even worse in LLMs because it takes a long time to start up. So a lot of what you're trying to do is you're trying to experimentally verify the constant that, given a certain increase in the amount of traffic, will keep you below the critical point of having to start rejecting or tossing out requests, or, you know, having, you know, huge problems at the model server. Now the nice thing is model requests are small, so in theory every request is retriable today. That's another factor I think that we, you know, if we talk about like pulling out things here, critical points, thresholds, constants, selection, but also are we leveraging compressibility was the previous one, but the next one I think is, as you're saying, are we leveraging statelessness of requests? That's something that Kubernetes itself does not do today. I will point to the discussion in serving that was happening this week about LLM gateways. A lot of the LLM gateways out there don't do anything about directing traffic to individual model instances. One of the things that we've discussed as I was thinking, or a few people have brought up this already, is there are advantages to queue management and stateless hedging, or, you know, hedging and identifying load and shifting traffic more rapidly by canceling requests in flight and moving them to deal with hotspots. So if certain requests are generating lots of output on one server, but not a lot on the other, you can make a choice afterwards, take the latency hit, but you achieve better overall. The auto scaling is about how many horizontal replicas. The next level up is how do you use those replicas as a part of a system? Maybe that's a follow-up discussion for if that's a different working group for that gateway side, but it would be how do you balance traffic and cancel traffic? I guess we wouldn't do it in this work stream, but like we're already talking about it. So that's another one is managing the queue at a greater than one instance size. I guess
I saw
again,
an interesting blog from Character AI today on their serving system. I just posted it in here, and like they're operating at like massive scale. So I obviously like think that this is like really overkill relative to like an enterprise deploying a model, but they have like a pretty sophisticated like prefix caching scheme, and it's really important for them. And like as part of that, they need to like route requests to specific servers. And like VLM supports prefix caching, for instance. So like this would be something like in the AI gateway where like if you have like a back and forth between the model, or like you somehow know that like a particular request has prefixes that are already cached in like one of the servers, this could be something that's like a useful feature. So
we've I put this in a couple of places. Is I think there's kind of I've seen this in a few research papers. I think characters use cases hits it, and there's some belief that there'll be more statefulness in models, and part of that's just each models are running on accelerators. Accelerator memory is so far away from everything else that there are advantages the bigger and the bigger caches and models get for particular requests. Like the longer your context is, the more KV cache you have, the bigger your KV cache is, the longer it takes to transfer it somewhere else. So even though we're not stateful today, there's the session proxying, from old Java days where you got 5-minute long requests to carry out cross two-phase transactions across database systems is going to come back with stateful eventually, just based on how far away model memory is and how big memory is. So that I think that's a good one too, because like for Cube, like when we're talking about overall problems we have here, Cube deployments kind of work with the assumption that everything is fungible. Stateful sets work from the extreme opposite. This is an example, I think, of the problem is we have more affinity type use cases, even though everything is stateless. We'll want to think about, are all replicas equal? So I know there've been a few requests already on auto scaling around scaling down the right instances. So I just wanted to connect those threads here to that comment. Maybe if we're going to be actively managing the replicas, the next question would be, or number of replicas to support traffic. If session affinity becomes even more common over the next year or two, the idea that you might preferentially also think about which instances to scale down means we should start thinking about the pod deletion cost and the various ways we have of scaling down specific instances as a requirement as well.
Yep. And the last thing I just wanted to say, back to the point of like how quickly to scale up, like I do think like when I'm talking about these critical points, these are very much like when you get to equilibrium kind of ideas where like the x-axis is request rate, the y-axis is overall end-to-end request time. And like when I'm talking about these charts of like very slow increase in request time and then all of a sudden big uptick, like those are as measured by like the different query per second rates once you get to equilibrium. And so like one advantage I do think that we have is like in the context of auto scaling, there's usually typically more of a gradual change from a low request rate state to a higher request rate state. I mean, it depends on like, I guess, the pattern of the workload and maybe this isn't always true, but like, especially for something at scale, like if OpenAI is running their server right now, like they're unlikely to see huge jumps up in traffic very quickly and then huge, decreases from there. And, given the length of the average end-to-end request, like I do think we are very likely to move in the average case pretty slowly from one request rate to another. And so I do think like, obviously like it will take a long time for the servers to start up, but I do think that is one like other piece of nuance. Like if we move from request rate 1 to request rate 5 over the course of like 30 seconds, it'll take the server like a minute or so to get into equilibrium where the queue starts to back up. And so, that's another thing that I like about queue as like a metric for auto scaling on is it's very much forward looking, as it relates to, when you want to scale up in comparison to like time to first token, it will be more of a trailing metric that like once you're in this bad state, if it's taking 5 seconds for your request to start, like that's kind of a bad sign. And the server's already in an unhealthy state. Whereas like when you're transitioning from healthy to unhealthy equilibrium states, the queue will be like a leading indicator of like moving from one space to another, I guess. Yeah, go ahead.
Justin.
Hey, thank you. I just joined the mailing list, so I hadn't joined in these before. I had a meta question if we have time, which is, what is the expected output of this working group? I was looking through the notes and I didn't see it. Like, is our goal to produce blog posts? Is our goal to produce a benchmark? Is our goal to produce a reference implementation of serving that we can then compare against?
So you mean the working group or this work stream of the working group?
Let's do both.
So this work stream, what the original goal here was to identify gaps in the Kubernetes primitives that would prevent the use cases from being successful. And like we Google has some experience, and various folks have shared theirs. We talked about node auto scaling in one of our previous work streams. Where are the operational gaps? How is this use case different that the kube primitives are inadequate for? I'd say the overall working group fits in the understanding and getting people aligned so that we can suggest changes to Kubernetes that address the differences in the new class of workload that kube is inadequate for, because unlike some previous workloads, this one is probably going to be as big or bigger than most of the existing workloads that are running. So it has a little bit more outsized argument for changing kube.
I guess my question would be, as software engineers, without biasing, do we want to have that discussion in blog posts, or do we want to have that discussion in benchmarks in code?
I think that's a good question, because some of this is actually making sure, like, kube is about consensus. How do you get consensus? You get a bunch of people who have the problem to show up and make sure that the problem is well solved. I don't always know that we have that consensus yet. That's part of one of the goals of the serving working group, is to bring that consensus. So Justin, like, are you advocating for something specific here, just in terms of like?
I think we can talk a lot. I think it is very difficult to reach a conclusion and a recommendation without some form of objective truth, be that a benchmark or be it working code, like a reference implementation. I don't want to say we're going to compete with everyone doing like, serving infrastructure, but like we should be able to say, here's one way to do it. Here's where kube falls down. If we were to fix feature X of stateful sets, we would get a 10% boost, and therefore it is worth it or not worth it. And I think then we could say, you should use this proprietary or this other serving infrastructure because it is 50% better on this metric, which we've collectively defined.
One of my data points is that everybody who is actually using kube to serve, everyone runs their own benchmarks independently and makes decisions based on those benchmarks. And so there is no objective truth, because everyone's subtly different. Getting the language and terminology that we could all agree on, I think, is a outcome of this. For instance, suggesting queue depth, getting Rob's feedback, suggesting it is. Do we all agree what a queue is? Do we all agree what the model server would do? But I think that's actually what I've noticed, and maybe if other people have noticed this as well, is that I see benchmarks produced all the time without giving any clear statement as to whether this was at constant latency. Given that latency is such a strong, what I hear, everyone's looking to hit a latency target. Any benchmark without describing the latency conditions is basically not a benchmark. It's you ran two numbers and showed me some output, but I don't know whether that's useful. So I think maybe then, Justin, to your point, what can we do to bring that common definition? What are we actually trying to optimize for? And Robert, you're saying not throughput or not over-tuning the model servers, but ensuring that we're getting the traffic to the instances by spreading them out at the right thing. And then we have a common definition of queuing.
I heard Robert say tokens per dollar. I think you would add at a particular latency threshold, but that seemed like I can't game that. I can game everything else, right? I can game queue depth very easily. I can start serving from CPUs, right?
Okay. Cost can be a little problematic because everybody pays different rates, but everyone can. So you can't compare two different people on cost per dollar for what they achieve as their cost, because that cost comes if they're running the LLM themselves, that's their own cost. But you can compare it on fixed hardware, and that is maybe a close proxy for dollar.
We can always put a notional value on an average price on like various clouds.
I think we're at time. There's another session booked for next week. Hopefully we can continue this discussion, but thanks everyone for joining, and see you again next week.